Okay. Oh, by the way, sorry. Previously, this was I made an error. No, this is not R tilde. This is R.
Yes. Yes.
Sorry. Yeah, this was supposed to be R. I mean, you can easily see that this is supposed to be R because, yeah, because you have these delta factors in front, right? So you basically have your dt is going to be equals to du minus dr tilde, but then this is going to be equal to du minus where previously we're solving that dr tilde is equal to delta minus 1 dr. So then that means that this is delta dr, and that cancels the delta in front of the du. So sorry. So anyway, so this is supposed to be dr. All right. So right. So for the infalling, we know that we're going to have the infalling. It's always just horizontal. Now, of course, the important thing is the outgoing. So for the outgoing, of course, we know that for outgoing, this is delta, and so delta is supposed to be r minus r plus minus r minus. And therefore, we see that when r is bigger, so when here r is bigger than r plus, and of course is bigger than r minus, this is just going to be positive, right? So that means that this is the ingoing and this is the outgoing, so it's just going to be some positive, and therefore this is our future direction, right? So here the discussion is the same thing. Once we enter r plus, once we enter r plus, the outgoing is going to be this. So now our future is completely inside the horizon, right? So once you go inside, it's going to be start to get negative slope, and therefore your inside your future is always inside the horizon. Okay, but now you guys see that there's actually something interesting now, because once you go into here, so when r is smaller than r plus and bigger than r minus, your horizon is always, your future is always in this direction. But once you go past the inner horizon, so let's call this outer horizon, and let's call this inner horizon. Once you go inside the inner horizon, both of these are minus, so you get plus again, right? So that means that you go back to having something that looks like this. Okay, what does this mean? This means that we have a singularity here. This means that we, in contrast to the Schwarzschild solution, for if you actually trust the Reisen-Norton solution, we don't actually necessarily we don't necessarily hit the singularity. Hit the singularity. Okay. In fact, what you can see here is that once you go in, it looks like once you go into the horizon, you're forced to you go into the horizon, you're forced to go to r minus. But once you pass through r minus, hey, you can jump back into the horizon again. Okay, so to understand the faith of actually what's going on, we should really use a better coordinate, which actually, because as most of you know, that in these Finkelstein coordinate systems, your horizons, your r plus and r minus, is still an infinity. They will generate infinities here. So we want to pull them back, and therefore we go back to our Kruskal coordinate. Which will allow us to pull all the infinities into finite value. Okay, so for Kruskal coordinates, we're going to have, let me introduce u plus minus. So we're going to have two sets, either u plus or v plus, or either u minus or v minus. Okay, so the definition is u plus minus is going to be equal to plus minus exponential k plus minus u, and v plus minus is going to be equal to negative exponential minus k plus minus v. Okay, so because when we're at the horizon, the u and v will all go to infinity because well, I mean, you can see it here, right? Because we know that when r goes to horizon, r tilde will go to infinity and u will go to infinity. So we will really like to pull the coordinate system such that at the horizon u and v can be at the coordinate systems can be finite. Okay, good. So we're going to introduce the crucial coordinate, and it turns out that if you use crucial coordinate, now the horizon is going to be finite, but you're still going to have some finite values, but then you're going to have some singularities. So let's take a look. So in this coordinate system, in big U and big V, sorry, why can't I go? Oh, my iPad is not agreeing with me at all today. Okay. So in this coordinate system, first of all, we see that if you multiply u plus and v minus, v plus, then this is going to be minus exponential k plus u and exponential minus k plus v. And of course, this is going to be just minus r plus, r plus, r minus, r minus. This has an exponent, let me call this alpha, times exponential 2k plus r, where of course we know that well, alpha here is just r minus square over r plus square. Okay. Okay. So, and of course then we have the metric, which takes this form. So let me just write down the metric, r plus r minus. So once we write down the metric, we see that there is no singularity at r plus or r minus. So everything is regular, as we expect that those are just coordinate singularity. Okay. Okay, great. So in this coordinate system, we see that the horizon r equals r plus corresponds to u plus times v plus is equal to 0. Okay, so corresponds to either one of them to be 0. Okay, so that means that if we draw, let's draw the Kruskalov diagram again. Okay. So we draw again the Kruskalov diagram. This is exactly the same thing as we drawn before for Schwarzschild. So then we have, let me call this u plus. This might be a little bit different than what is in the textbook. I've switched u and v just to be consistent with our notation. So this is exactly the same. So we have u plus u minus. So here now we've successfully bring the horizon to finite value. So these coordinate, this is associated with v plus being 0. This is associated with u plus being 0. So this is the horizon r equals to r plus is here. So once again, so it's very similar. We start out with here where we basically have, this is r bigger than r plus. And then in the future, we move into the horizon r equals r plus. So this is r smaller than r plus. Now, what is different compared to previous case is that here, because if you remember that when we were doing things in the Schwarzschild case, we changed to the Kruskalov coordinate, and then we get all the way analytic, all the way to the origin, to r equals 0. Here in the current case, when we use this Kruskalov coordinates, we find that now we can freely go inside r smaller than r plus. but we cannot go to R minus. R minus has there's a coordinate singularity here in this coordinate. So in the cruise coordinate, we can only continue using this coordinate patch. We can only continue here to here. And it looks as if we have some singularity at R equals R minus. So there's appears to be a R equals to R minus singularity. Okay, of course, that's not a true singularity. It's just a singularity associated with your coordinate patch. So at this point, we can just switch to something else. We can just switch to u minus v minus, because if we look at u minus v minus, so let's switch to u minus v minus. If we switch to u minus v minus, then u minus times v minus is now going to be equal to r minus over r plus r. And then once again, we have 2k minus r. Okay. So if we switch to this coordinate system, now we see that, hey, this is regular at r equals r minus, and we can continue. But this is regular at r equals r minus, but it's going to be as a singularity at r equals r plus. But that's the previous outer horizon. Okay, so that means that we have the following picture. So let me just draw this coordinate system. So let's start with the original r. So let me call this r plus, r minus. Okay. So when we start with r outside, we can use any coordinate system we want. So we can have any coordinate system we want. Once we want to go past r plus inside, we use v plus v u plus. Okay, we go to u plus v plus. And in the u plus v plus picture, so in the u plus v plus picture, what do we have? We have that this region, let me call this region 1 here, was this region. And then we continue to region 2 here, and that is this region. And we see that in the front of us, we seem to have a coordinate singularity at r minus. So this seems to have a coordinate singularity here. So at this stage, we switch to another coordinate, v minus u minus, which after multiplication looks like this. And this tells us now we can further continue into past r minus. Of course, it's going to have a coordinate singularity in the back. Okay, so if you draw this, then in terms of v minus, sorry, this is u v plus. So in terms of u minus v minus, which is this coordinate patch, now we start to come in, and this is, of course, we start in at this region 2. And we can now go into this region. Okay, so this has an r plus single, so this has an r minus. This has an r minus previous that looked like a singularity here. And here, once we go into here, we see that there is actually a real singularity associated with r equals 0. So here, the r equals 0 singularity is here. And this, let me call this as area 4. Okay. So now we see that by using 3 different charts, so we start with the original solution chart, we then go to the Kruskal coordinate chart to get us past r plus, and then we use the second Kruskal coordinate chart to get us to past r minus. So remember that the Kruskal diagram is going to look very similar than the diagram that you would see if you use Penrose diagram. So if we do Penrose diagram, then basically this is what we will see. Okay, so by the way, do any of you know what, sorry, I've drawn this wrong. I shouldn't draw this to be r minus. Sorry, this is not r minus. So do any of you know in the new coordinate system what would correspond to this? What corresponds to these two axes? So what corresponds to these two lines here?
R minus.
Very good. This is R minus. Okay, and I should write this. This is R plus. Very good. Okay, so this is R minus and this is R plus. So that means that we can have the following. Have the following Penrose diagram. Sorry, let me draw this better. So we have the usual. So usually if we have short shot, remember that yesterday that the homework that you were supposed to do was to derive the the Penrose diagram for short shell that would take this form. Now where this is in the short shell case, and this will be your short shell horizon, and this will be R equals 0, right? The R equals 0 singularity here. Now for horizon northern, something changes. So again, we have the horizon here, but this is not the short shell horizon because we have two horizons. So now we start with this. We start with this here. So that means that here we have the R plus horizon here. Once you enter the R plus horizon, you can now switch to this coordinate system. Where in this coordinate system, now you have the R minus sitting here. So that means you have something that looks like this. But here, these are the R minus coordinate. So let me just use a different color here. This was the R plus coordinate. Here, this is the R minus coordinate. Once you move into this diagram, you see that now the singularity is at R equals 0 here. So that means that the Penrose diagram that you'll find is that here these are the R equals 0 singularity. Okay. But remember before we discussed that actually because once you pass R minus, because of the fact that your future horizon changed, that looks like as if you can actually jump back into R minus, right? Because previously in the short shell case, once we enter the horizon, the future is always pointing towards the singularity. Now the horizon is R plus, so once we enter R plus, the future is always pointing towards R minus, not the singularity. And once we pass through R minus from the Eddington Finkelstein coordinate, we see that actually it looks like it's not necessary that we have to go into the singularity. It seems that we can jump back into the R minus. Now in this Penrose diagram, you see actually what happens. So here, once here we know that we must go into here. But once we go into here, we can just pass through R minus. We were forced to go to R minus, and we pass through here. But once you go to R minus, because of the fact that in the Finkelstein coordinate system, that the future no longer points towards singularity. This means that it's no longer true that you'll hit the singularity. And in fact, you can jump back into R minus. But in this picture, you actually see a very interesting thing. The fact that you jump into R minus, you're jumping into a region. You're not really going back. You're actually jumping into a new region. So in this new region here, basically what happens is that you have a new analytic continued space-time. Okay, so now this is your R plus again, this is your R plus. Okay, so this is an analytic continuous new space-time. So basically, so let me just draw this in a better form. So basically you see that this and the Penrose diagram for the Penrose diagram. So let me just draw here. So the Penrose diagram for the horizon northern black hole is an infinite copy. It's actually infinite, and it has an infinite analytic continuation. Sorry, this is a little bit, my drawing is a little bit bad. And so on and so forth, okay? So you start from here, you go past the R plus horizon, you go inside, you go through the R minus horizon. You can choose to either go to the singularity here, or you turn back to go to another R minus horizon. So let's label the R plus. So let me label the R plus with red and R minus with blue. So we first pass through R plus the outer horizon, and we go through the R minus inner horizon. But once we go into here, the causal patch allow us to go through another R minus horizon. But this is not the same R minus as before. It's actually a new R patch R minus. So you go through an R minus and then you come out exactly through an R plus, you come into here. And of course, once you're outside, you can choose to go into a new, but this will be a new R plus here. And then you can go through an infinite patch like this, okay? So this is the interesting causal structure of Rice-Northern black hole. So it's very different, Rice-Northern black hole. The statement is that it's not necessarily true. It is true that once you enter the horizon, you cannot come out. But once you enter the horizon, it's not true that your fate, you must ultimately hit the singularity. You can actually, once you pass through the R minus, you can actually come out, okay? But this is a very interesting question, because that means that, remember that, let's compare to the two Penrose diagrams. So sorry, let me just draw a new one. So if you remember, so as I mentioned, the Penrose diagram is useful to talk about the ultimate causal fate. So in flat space, so let's compare. So in flat space, the Penrose diagram look like this. And so basically, remember that we have I plus infinity, and this is scribe plus. So for null rays, we must end up here. And for massive geodesic, for example, you must end up here, right? So irrespective, so once we start, we already know that the final fate of the final fate of where we're going. In the short shell black hole, remember last time that after the Monday lecture, we know that our space-time looks like this for the short shell black hole. And we know that you can either, so this is I0. And so you're either entering here, you're either hit here. Of course, for light rays, you can still hit scribe plus. But if you enter the horizon, you must hit here, which is a singularity at R equals 0. This is the short shell black hole. Now, for the Rice-Northern black hole, the Rice-Northern black hole, the causal structure is now different, right? Now we have with its infinite continuation. So let's say if we have something that's set up here. So let's say we have something that's set up here. We must go into here, but then once we pass through here, it's not clear whether or not we're actually hit the horizon, or actually you can hit the R equals 0 singularity, or you can come back out to another R minus. So this causes a problem, because this is the problem here is that once you have, so people usually we think about physics as deterministic, which means that usually in terms of causal structure, that means that usually when we think of, if you slice open here, and let me call this, usually we call this a Cauchy slice, which means that in principle, so for example, here, if I set up here, I know all the, wherever I am on this Cauchy slice, then in principle, I know my fate completely. It's completely deterministic where my fate is. Now, once you have this, so let's say you determine here. So you can determine where you're starting out here, or which direction you have, whether you're null or whether you're a time-like geodesic. Then you can evolve your configuration. But the furthest you evolve is that you can evolve to R minus. But once you pass R minus, the final fate is not clear. So you need information about what happens here, and after you pass through R minus to determine the future. Okay, so this causes a problem, because that means that setting up the initial data here is not sufficient to determine what is your final fate. So in other words, deterministic evolution is broken down by this R minus. So this R minus, which you'll see in the literature, is often called Cauchy horizon. So it's after passing this Cauchy horizon. So after passing this, there should be the physics that you have is no longer deterministic. And or said in another way, after passing this, you can find various different solutions to the Einstein equation with the same initial condition, but they have different end path. Okay, they have different endpoints. So this is what, so I'll send, so after today's lecture, I will send you some supplementary material. You can read about this in popular magazine. So this is related to, there's a conjecture called strong cosmic conjecture, which is that the following. It's saying that, of course, all of this that we've discussed is just solution to Einstein's equation, right? Einstein's vacuum equation. So if you just add in any matter, many of these structures might be no longer true. Many of these discussions. So in particular, if you think about it, if you go back to this infinite diagram that we have, if we have R minus, then in principle, it's saying that all of these infinite sequence of the past. So for any given R minus here, so let's say you have an R minus here. So for given R minus, you have an infinite sequence of path of information that is passing through R minus. So that means that at R minus, there's infinite amount of information that are coming in. And therefore here, there's supposed to be large perturbations. Or in other words, this is just extremely blue shifted around the R minus region. So that means that it's very likely that this R minus horizon is actually non-stable. Okay, so this is a conjecture of Penrose, which is saying, so the strong cosmic conjecture, which is a conjecture of, once again, in Penrose. And the statement is that actually, if you do perturbations around this R minus, you'll actually see that R minus appears to be non-stable. Well, you'll find that R minus, this Cauchy horizon should not be there. And the way that you see it's not there is that you'll see that this is a non-stable horizon. Okay, and of course this is a conjecture, and this remains to be proven. And actually, so there's many recent developments along these directions. So I'll send you some references. In particular, I will send you more like a popular science discussion, which actually shows that mathematicians have been actually able to prove that the Cauchy horizon is actually stable. Okay, in contrast to what the Penrose conjecture, they show that actually the Cauchy horizon is stable. However, there's some intricate issue with this Cauchy horizon, with the horizon at R minus, such that even though it is stable, but in spirit or in reality, there is still you can still maintain deterministic. Okay, and so I'll just leave this. So it's very interesting. So you guys can look at it. But this is still an ongoing research about what actually happened as the R minus Cauchy horizon. Okay, but I'll just leave it at that, and you guys can read the material, and we can discuss more if you're interested. Okay. So is there any question? Because if not, then we're going to go to the more realistic, which is rotating black holes. Okay, here for Royston Northam, this is a charged black hole, and basically what charged black hole gives is you have R plus and R minus. You have two horizons, and essentially, in some sense, R minus replaces the original singularity in the sense that R minus, your fate, once you go through R plus, you must go to R minus. Just like whenever we enter Schwarzschild black hole, we must go to the singularity. But in contrast to Schwarzschild black hole, once you go past R minus, it's no longer true that you must go to the singularity. And this causes a lot of interesting causal discussion, which is related to this Cauchy horizon. Okay. Okay, great. So now we're going to more realistic black holes, which are rotating black holes. Okay, so now we move to rotating black holes, and this will be the more interesting kind in the sense of reality. So so once again, we've discussed this black hole solution at the beginning of these lectures before. So we're just going to give it very briefly. And of course, for both of these solutions, you have extremo solution, near extremo solution, where the R plus and the R minus degenerates. So the solution is you don't have extra Maxwell fields, it's just this. But instead, because you're talking about rotating solution, so that means that your metric is no longer, in a sense, diagonal. It's just going to have mixing term with the phi direction, where phi is defined as the rotating direction. So here, in principle, we're going to see similar structures before, where we're going to have inner and outer horizon. But the difference, importantly, is because you've broken spherical symmetry, and therefore, as you can see, the dt square is not necessarily the inverse of the dr square. Okay, so here, once again, we have delta is going to be equals to r square minus r naught r plus a square. So this is again a quadratic equation. So you know that there's two roots. So once again, we're going to have r plus, and then we're going to have r minus. So here you see that from the singularity, you have both r plus and r minus. So you have two horizons again, the inner and the outer horizon. Okay. Now rho square, on the other hand, is going to be r square plus a square cos square. Okay, and of course here r plus minus is just, we discussed this before, is just r Schwarzschild plus minus square root r Schwarzschild square minus 4a squared. Okay. Okay, so we see that because of this delta here, because of this delta in the denominator of dr square, we again have a singularity, but this singularity only happens when r equals, sorry, what am I writing? This is minus. Okay, when r is r plus or r equals r minus. Can anyone tell me, so what about, is there a coordinate thing? So what about here? Can this be 0? So is there the usual r equals 0 singularity? Is r equals 0 a singularity for this black hole?
No.
No, right? Because when r equals 0, this is not a singular. You have a squared times cos squared, right? So actually, the usual singularity that you're associated with, that are associated with Schwarzschild, the r equals 0 singularity, now appears differently, right? So this r square is only, rho square is only 0 when r equals 0 and what? Theta equals plus minus pi over 2, right? So what does this mean? So first of all, what is the singularity associated with I mean, what is the structure of the singularity? So the structure is, so to see the structure of the singularity, of the singularity is still at r equals 0. Let's look at the metric there. So if we look at the metric at r equals 0, the metric is going to look like ds squared is going to look like cos theta d phi squared plus sine. Oh, sorry, I think it's the opposite. Let me see. Yeah, it's the opposite. Oh, of course. So this is the metric when r equals 0. Okay, and since when r equals 0, this is the metric. This tells you that now you need to further fix the singularity as appearing at theta equals to pi over 2 here. So that means that this singularity is actually a ring with radius a. Okay, so one of the interesting thing here is that you have a singularity inside your black hole, but this singularity is actually not a point. It's no longer a point-like singularity. It's actually a ring inside. Okay, which is because of this rho square here. Okay, is there any question? Well, so of course we can also discuss the causal structure by going to the Eddington-Finkelstein coordinate, and just by the very fact that you have things are going to be a little bit more complicated, but it's just basically going to be the same story because your delta has r minus r plus and r minus r minus, and therefore the discussion is essentially same, just slightly more complicated. What is actually interesting here is, as we mentioned in the previous in the very beginning, is that there's going to be the ergosphere. So let's take a look. So notice that this solution here has two killing vectors. The solution has two killing vectors. Right? It has, let me call this KT, which is partial T. And it also has independence of K phi, which is partial phi. Okay. So if we look at the KT killing, the KT killing spinner. So if we look at KT squared, so let's look at KT squared. So sorry. Oh, I see. What do you mean that we of course we can define? I mean, phi theta, these coordinates are not the coordinate system. I mean, these are all independent coordinates, so you don't need to have a particular value of r to define theta and phi. I think the reason that you have this, you're asking this question, your question is because for you, when you think about theta and phi, you think about it as x. And then you project x down into, you have x, y, z, and x, y, z is related to r, related to r theta and phi in a particular way. And therefore you think that if you don't have r equals 0, you cannot relate it to x, y, z. I think that's the reason that you're asking this question. And indeed, but however, note that here we're just using a coordinate chart, right? This coordinate chart doesn't have anything to do with the Euclidean. In fact, it doesn't, because this coordinate system is not for flat space. Okay, and therefore you don't, I mean, therefore it's just a coordinate chart. You just have r, theta, and phi, and they're all independent. Once they're a flat space, they have this nice relationship with the usual Cartesian coordinate system. But other than that, they're completely independent with each other. Okay. So these are just independent coordinates. All right, so let's talk about KT square, because we know that KT square is going to be something that is, so let's say KT nu, G mu nu. Of course, this is going to give us, sorry, I think I'm supposed to do lower indices. KT nu, G mu nu, and this is going to be equal to minus rho square. So this is, of course, because these are killing vectors, and therefore these are supposed to be conserved quantities if you're following a geodesic. But let's just look at this. Okay, so this is its value. So you can plug in R plus. So if you evaluate this at R plus, if you evaluate this at R plus, then this R plus, if you evaluate at R plus, this is just A square sine square theta rho square. Okay, so importantly, this is bigger than 0. So this is actually space-like. Okay, why do I say this? Because if you remember, when you're looking at the Schwarzschild solution at the horizon, the killing vectors are actually null at the horizon. Here at the horizon at R plus, the killing spinner is actually space-like, which means that you can define a killing horizon, which is defined as, so I think we defined this in the very beginning. So we can define the killing horizon, and that is that which is defined as KT mu, KT nu, G mu nu equals 0. So that's defined when the killing vectors square are null. Okay. And of course, then you're just defining the 0 of this, right? So if this is null, then that means R must be equal to, that means your killing horizon is actually at R equal to R Schwarzschild plus minus square root R Schwarzschild square minus 4a square cos theta square over 2. Okay, so this is the killing horizon. Okay, and of course it depends on theta. And so this is the structure that we've drawn before, which is in the at the very beginning when we were talking about not today's class, but previous class when we were talking about rotating black holes. Once we have this rotating solution, where here this is given by R plus, then you actually have a killing horizon that looks like this. So let me call this RK. So let me call this RK plus minus. So this will be RK plus. Okay. Because it's RK plus, because I mean this is outside of R plus, because when it's not theta, this is actually smaller than 1. And remember that R plus minus is without this without this cost factor. This cost factor is not there for R plus minus. So that means that when theta is at pi, when theta is equal to 0 or pi at 0 or pi, this R plus minus is going to be equal to R plus K, the killing horizon. At theta equals to 0 or pi. These are the same, but when thetas are not 0 or pi, R plus is basically generically smaller than RK plus, and R minus is bigger than RK minus. But today we're just going to focus on RK plus. So we have actually the black hole has an interesting structure, which is that you have actually this area, which is actually outside, which is this area here, which is outside of your horizon. So this side is actually outside of the horizon, which means that from causal structure point of view, you can come into here and go out, no problem, because you haven't went into the horizon yet. And so we're actually going to discuss what happens when some interesting properties that happens when you actually choose to come in and then come out. So this area here is what we mentioned before, is called the ergo region. Okay. Okay, so let's see what happens. So let's consider for this rotating black hole. So for this rotating black hole, let's consider a null line. Or null geodesic. So let's consider at fixed theta. In particular, we're going to set theta equals to pi over 2. So basically, we're going to consider something here on the equator. Okay, and we're going to release this null line. And since we're fixed some place here, and then we're going to release this, so we're going to shoot a light ray out. So at the very beginning, so if we shoot a light ray out, so at the very beginning, dr is going to be just 0. Okay, so you're going to shoot a light ray out, let's say here or here, any point. You're just going to shoot a light ray out, and at the beginning it's going to be 0. dr is going to be 0. So that means that ds squared, which is a null geodesic, is going to now be, so I mean, we're just going to write it out. So it's just going to dt squared 2 times gt phi dt d phi. We don't need to write down the explicit form of these coordinates, and plus g phi phi d phi squared. Okay, so the null geodesic, if you're on this null geodesic, which of course this light ray will follow, then that means that your d phi dt, right, you can just divide everything here by dt squared. So if you divide everything here by dt squared, you're just going to get g dt plus 2 times gt phi d phi dt plus g phi phi d phi squared dt squared. Right, and then you can solve for d phi dt. So you can see that what we're doing is we're shooting a light ray on the equator of this rotating object, and we're trying to follow this light ray, see where it's going. Okay, and you'll find that the d phi dt, of course, is going to be equal to negative gt phi over g phi phi plus minus square root gt phi g phi phi square minus gtt over g phi phi. Okay, now at the horizon, so at the killing horizon, if you remember, the killing horizon is defined by this k squared go to 0, which, if you remember previously, the k squared is just this factor here, where this factor is exactly, this factor here is exactly what is sitting in front of dt squared. So if you think about, so let's see, so let's just work this out. So here dt squared, so dt squared is multiplied by minus rho delta, but then you also have this term here, which is plus rho squared. Oh, sorry, I think this is let me just make sure. I think I probably was a little bit too fast with this on the form of the metric. Yeah, I think I'm missing, yeah, sorry, this was supposed to be a rho square. Yeah, so we have rho square here, and then we have rho square a square sine theta, right? And so if we sum this to, so the dt square is going to be the thing in front of dt square is going to be minus delta, which is this minus r squared minus plus r naught r minus a squared plus a squared sine theta. Okay, so it's just going to be minus r squared plus r naught r minus a squared cos theta. Okay, so this is exactly, this is the term that, yes, this is a term that we have here. And therefore, on the killing horizon, so basically on the killing horizon, you're going to get GTT go to 0 on the killing horizon. Okay, so at the killing horizon, you can show that. So it's basically just at the killing horizon is just going to be either 0 or there's going to be minus GT phi over G phi phi. Which if you plug this in, you're going to get either 0 or 2a r naught squared plus, r short shell squared plus a squared. So you're going to have two solutions. So what does it mean? So remember, so I'm just sending out this light ray. So the light ray, the change of this null coordinate, this null line with respect to time in terms of phi, you're going to have two solutions. One is 0. The other is some fixed value that is proportional to a. So can someone explain to me, why do I have two solutions? This is a very simple physical picture. Why do I have two solutions? Anybody have any idea? I'm here, I'm releasing the ray, and then I'm seeing where this null ray will do. When I'm at the killing horizon, which of course everything is null, so things are supposed to be nice here. So my null ray will have a rotating, of my angular, my axial angular coordinate with respect to time and some fixed rotation. So here basically we're saying that there's one that has a fixed angular velocity. So this is a fixed angular velocity of something that is, of course, independent of theta and independent of phi. So it's a fixed angular velocity. And the other is the angular velocity is 0. So can anyone tell me why? Any guess? Let me see if there's any comments in there. No, no comments. Can you, do you need a hint? Or you need a break? Okay, raise your hand if you need a hint. Okay, very good. Yes, someone answered. Indeed, this is because of the fact that the black hole is rotating. So this is really telling you that the black hole, the rotation is actually dragging the space-time here. Okay, so in one direction is indeed rotating together. So this is what is called the frame dragging effect. Okay, because of the fact that the black hole is rotating. So that in one direction it's rotating against, the light ray is going against the rotation, the rotation direction. The other is just going with the same direction as the black hole is rotating. So basically the fact that you actually see d phi dt is going to 0, this actually tells you that the entire space, the local frame, is being dragged along as the black hole is rotating. Okay, so you have this, you can actually see this, what is called the frame dragging effect. Okay, Of course, this means that, so now you can actually see that why do we actually call this A related to the angle? We think that A is related to the angular momentum. And in fact, we can, so instead of computing d phi, we can compute actually the angular. So if we want to define the angular momentum of the black hole, we should really compute this velocity, this angular velocity at the horizon. It's not going to be zero, right? It's going to be rotating at the horizon. So we can define, let's do, so at the horizon, d phi, we can compute d phi d tau at the horizon, r plus. So times r plus, and we can define this at the, we get h, the angular momentum of the horizon. And in fact, we can compute d phi dt. Oh, sorry, we can just call this the angular velocity. Let me just call this angular velocity. Okay, and we can show that this is sorry, no, I already multiplied this with r plus angular momentum. So this actually, let me just directly quote the answer here. So this is actually just a over r plus square plus a square. Okay. Okay, now, let me see, what should I move on to next? Okay, so great. So now equipped with this, we can talk about what is called the Penrose process. And that has to do with, so that has to do with the fact that you have two killing vectors. So remember that we have two killing vectors. We have k, let me see, what did I call it before? We have kt and k phi. So we have kt, which let me call this kt, which is partial t, and we of course have k phi, which is partial phi. Now, equipped with kt and k phi, that tells us that we can define two invariants associated with our geodesic. So we can define minus kt mu dx mu d tau. Right, this should be conserved. And we're going to have, let me call this L equals to k phi mu dx mu d tau. So both of these things are conserved. As you can imagine, why do I call this energy? Is because this is the time-lag killing vector. Okay, and the reason I'm calling this something like the angular momentum is because this is related to the rotation angle. Okay, good. Now, since as we've discussed before, K inside the horizon is actually space-like, whereas outside the horizon, sorry, when K is at the horizon is actually space-like. when K at the killing vector at the killing horizon is actually null, right? So that means that actually what we can have is we can let's consider a construction which looks like this. So remember that we had a black hole and we had the killing horizons here. And when we went to the ergo region, so here K square was here K square is equal to 0. Here K square is actually bigger than 0. So that means it's space-like. So that means that E, when E is outside, of course, when E is outside here, E must be bigger than 0 here. But when going inside, E actually can be smaller than 0. Okay, so that means that, hey, in principle, this is what can happen. I can have something that is, so let's say if we're outside here, outside this region. Now, let's say we have two objects and they each contain E1 and E2. Okay, which is total E0. Okay, then we can let this go inside the horizon. So let's inside the horizon, meaning go inside the right. Sorry. So let me not separate two things here. Let me just start with being outside. So being outside, I have E is just bigger than 0. Let's just start with here. Then when I go inside the killing horizon, remember that I'm just going inside the killing horizon. This is not the event horizon. So that means I can still come out. So if I actually go in the killing horizon, but in the killing horizon, each object can now become E has -0 because of the fact that my killing vector is actually now becoming space-like inside the killing horizon. So that means that I can choose to have separated into two terms. So let me call it E1 and E2. Inside the killing horizon, but E2 is smaller than 0. Okay, but of course, because E is a conserved quantity, so this still must be equal to my original E. Okay, so let's say if you go in and you separate into two terms. So for example, you throw a rock, okay, and you aim the rock in such a way that allows you to have the corresponding E2 to be smaller than 0. And after you aim this rock, you threw it, you threw out this rock, you come back out. Then after you come back out, what you're getting, because E1 plus E2 must be bigger than must be the same as E. Therefore, you conclude that E1 is actually bigger than E. So in other words, you have some energy, and then you go into the killing horizon. And because of the fact that the killing vector becomes space-like inside the killing horizon, it becomes the E can be actually negative. So just aim such that your E is negative, but because the sum has to be conserved, because remember, we're talking about a conserved quantity. And since the sum has to be conserved, that means that the remaining E1 once you come out is actually bigger than E. So you actually gain energy by going into the killing horizon. Okay, and this process is what is called a Penrose process. Okay, where you can actually go in and then you can throw things away which has negative E, which allows you to increase energy. Okay, so this might seem weird, but actually it's not weird because you actually have two conserved quantities here. Okay, so actually what is happening is that you can show that if you actually do throw this into the horizon, then what you'll find is actually that you'll find that actually the angular momentum has to decrease. So in other words, the energy that you're getting out after you come back out of the black hole from the killing horizon is that the black hole is actually now slowing down. You're picking away some of the angular momentum. Okay, and to do this, to see this, all you have to note is that you actually, because of the fact that you have two killing vectors, you can have a composite killing vector. So of course, if you have two killing vectors, you can do linear combination, it will still be a killing vector. But you can show that if you have x mu, you can show that if you have x, let me call this chi mu, which is the new killing vector, is given by kt mu plus this angular rotation factor associated with the horizon times k phi mu. Okay, then you can show that k mu is actually null. Okay, so basically this is actually null at the horizon, at the real horizon, at r equals r plus. Okay, and that is why, actually, that is one of the reasons why we call this the angular momentum of the black hole, because this corresponds to the null geodesic at the horizon. Okay. Okay, great. Now, since this is null at the horizon, so since this is null, okay, we can show, and because this is null and this is future pointing, we can show that if P2 mu, if we have this second thing that you're throwing into the horizon, it actually throwing into the event horizon, we can show that that means that if it actually enters the event horizon, that means that P2 mu dotted into X mu has to be smaller than 0. This is just to ensure that both of these, because X mu has partial t, so it's in the direction of partial t. And so P2 mu, in order for it to enter the horizon, the horizon, it wants to be future pointing. So that means it's also in the same direction of time. And because the contraction has a relative minus sign, so that tells you that this always has to be smaller than 0 if this is future pointing. Okay. Okay, but remember, what is x mu? So x mu is a linear combination of two killing vectors. What is P2 mu? P2 mu is just m dxt2 mu dt, or d tau, right? So this contracted with this tells you that what you have is that you have that the angular moment, the angular momentum associated with this thing that you're throwing into the horizon must be smaller than E2, the energy associated with the second thing that is thrown in. So that means that if you've arranged such that the thing you're throwing in is smaller than 0, this tells you that the angular momentum associated with it is also smaller than 0. Okay, and since once again, angular momentum is a conserved quantity, so that means that the black hole angular momentum is going to add an extra angular momentum here, such that it becomes 0. Sorry, such that it decreases because this is becoming smaller. Okay, so that means that the black hole is going to have a change in mass. Of course, the change in mass is going to be E2, and the change in angular momentum of the black hole is, let me call it, is going to be L2. Okay, and this relation, this linear relation, just tells you that the change of the angular momentum times the orbital, this angular factor associated with the horizon must be smaller than the change of the black hole mass. So the black hole mass is now decreasing because your E2 is going to 0, and your angular momentum is also decreasing. Okay, and that's what the Penrose process is. So the Penrose process is that you go in. So since you have two, conserved quantities, you can trade one for the other. That's basically what it means. So you can go into a black hole. First, you go into the killing horizon. Once you go into the killing horizon, then you throw something at the horizon, but you want to aim it in such a way that actually the thing that you're throwing actually has negative E. If it has negative E, then it's going to have negative, if it has negative E, then it's going to have negative L. If it has negative L, then it's going to slow down the rotation of the black hole. You come back out with more energy, and in some sense, the black hole shrink a little bit and it slowed down a little bit. Okay, so in some sense, you're actually extracting energy from the black hole. So this is a little bit like Hawking radiation, except that this is something that you can actually control. Okay, and this brings us to a very important fact, which is that the area from this process, you can see that the area, it seems that the area of the black hole never decreases. So the area of the black hole, so the area is associated with the area of the black hole associated with the area of the event horizon. So let me call A, which is the area of the event horizon. Okay, and it's given by 4 pi r plus square plus a square. This is the event horizon. Okay, so of course you can write it out. So it's going to be equal to, if I normalize this by, okay, so it's going to be equal to 8 pi g square times, of course, m square plus m to the 4 minus jg square root. Okay, where now I'm writing things explicitly in terms of m and j. So j is just going to be equal to m times a. So I pulled out the g. Previously, we were writing the solutions in terms of short shell metric, but now because we're going to look at the change in mass and the change in angular momentum. So we're writing everything in terms of mass and angular momentum. Okay, when you write things in this way, you get that the change of area, variation of A, okay, is going to be equal to, you can compute this. So it's just going to be equal to 8 pi g square root of g square m square minus a square times m, okay, times inverse variation of m minus variation of j. Okay, but now you see importantly, so the variation, the change, of course, this is just the change of mass and the change of angular momentum associated with the Penrose process of throwing something in. But you can see that since this was really derived from a composite killing vector, which of course will be conserved for generic geodesic. So you'll expect that this relation is generically true for any process which corresponds to something falling into a black hole that changes its angular momentum and mass. But at any rate, if this is true, then that means that the variation of m minus delta j times rho h will be bigger than 0, which means that the variation of A is actually always bigger than 0. Okay, so this is a very important thing. It seems that the area in these processes, if you have geodesics which are associated with things that are falling into the black hole, the area of the black hole always increases. Okay, and this is associated. This is really where people started to think about black holes as a thermodynamic object. And of course, many of you heard about Hawking radiation, the black hole temperature, and the various discussion is really stemmed from this observation. The engineering process is associated with black hole. The variation of A, the change of A is always increasing. So in other words, A seems to be as if it's an entropy of the system. Okay, and in fact, this formula can be rewritten in something that is very similar to thermodynamics, which is if I identify, let me see, if I identify this quantity here, if I identify this quantity here as, let me call this KT. No, KT is already for the time-like killing vector. So let me call this as just K. Let me just call this as K for this quantity here, okay? Then you have the formula, you basically have the formula that variation of, can invert this, and then you have the variation of M is equal to variation of A times K. Plus, of course, you're gonna have plus omega H times variation of J. So this is a little bit like the work that you have, and you can compare this to the thermodynamic equation where you have dAu, the change in energy, is equal to TdS plus work terms, okay? And you can see the similarity. First of all, we know that in an equilibrium system, T, it must be a constant. And indeed, for a black hole, K, which is actually sometimes called a surface gravity. So let's look at what K is. K is related to this quantity here. And you see that K is just a constant. So it's a constant associated with the horizon. So it's very much like temperature. Variation of A always increases, which is like the variation of your entropy, which is always increasing. So this is the second law of thermodynamics. And of course, there's also the third law, which tells you that the temperature in any physical process, you can never get the temperature to be zero. So that which should corresponds to K should never be zero. And let's see where K go, when does K goes to zero? So when K goes to zero, so K is the inverse of this. So you see that when K is equals to zero, it corresponds to G squared M squared equals to A squared, which exactly corresponds to the extremal limit, okay, or the extremal bound, or related to the fact that we discussed before, that black holes should not have a naked singularity. Remember that previously we say that A, when you normalize A with respect to GM, there should be an upper bound. It cannot exceed 1. And indeed, we look in the sky, we look at all these rotating black holes. We see that there actually is a maximum mass. Some of them are very close to 1, but they're never actually at 1. And this seems very eerily similar to the fact that T should never be 0 in a thermodynamic system. You cannot get absolute 0. So you cannot get absolute 0 surface gravity, which means that you cannot get absolute at extremal or go beyond extremal. But in black hole, the reason is for different reasons. It's because of something that we discussed before, which is that you should always have, you can never have a naked singularity. You should always have a horizon. Somehow this property can be connected to thermodynamic properties. And so this is why there's I think some of you may have already heard that then there's a large community that's been going on for a long time. So ever since people saw this, people thought that, okay, that means black holes should have an entropy. You should have an entropy associated with black hole, and the entropy should be proportional to the area if this holds. So that means that there should be an exact formula that can allows you to compute this equality. And there indeed, so Hawking and Birkenstein derived the Hawking-Birkenstein formula for the entropy of the black hole. And then there's various different developments. So since the entropy should be counting the degrees of freedom. So that means if you have a quantum gravity theory, the quantum gravity theory is going to give you the microstates of your black hole. So a standing challenge is to find a quantum gravity theory which gives the description of the microstates of the black hole, and then just count these macrostates, count the number of them, and show that indeed this counting actually gives exactly the Hawking-Birkenstein entropy formula. And indeed, of course, this was one of the very famous accomplishments in the early days of string theory, which is in string theory, you can use string theory to construct these black hole states. And since string is a quantum theory, you can actually count the quantum states in the string. And indeed, they exactly reproduce this entropy formula for black hole. Nowadays, of course, this has been generalized to many things, to quantum information. these ideas about trying to describe black hole spacetime using entropy associated with and associated with in quantum information, where we can also have entanglement entropy, and entanglement entropy then will have some properties associated also with these surfaces, sometimes associated with black holes, sometimes more associated with ADS space. Now, in one of your emails, someone mentioned about wanting to learn more about wormholes. So, of course, interesting, wormhole also comes into this the discussion of these into these discussion in the sense of discussing entanglement. And so, but of course, if I want to go into these directions, then will be much more hand waving than actually this lecture is already a little bit hand waving because many of these coordinate transformation I didn't give any detail. But if we were going to talk about wormholes and many of these research topics, there'll be much more hand waving. But if you guys are interested, so of course from here we can talk about ADS black holes, and then talk about once we have ADS, once we have ADS black hole, we can talk about ADS CFT, which talks about the black holes and ADS side. What does it correspond to? What objects? For example, you have thermal CFT, and then you can discuss the property of Hawking radiation using the dual CFT description. And since you have CFT, then you have entanglement entropy, which is associated with minimal surface and ADS side. Minimal surface. And then if we have distinct entangled area. So for example, you can imagine that you have some surface, you have this area that is entangled with this area. Then you can talk about wormholes that are connecting or rise. Okay, so there's many things we can discuss, but I think these are really more like storytelling, and there will be much less rigorous, even though today was not so rigorous. So we'll probably leave this to the end of the semester when the semester ends, and then we have more time that are not so structured, and then we can just go over these topics. Whatever you guys want to discuss, we can discuss more in a more free format. Okay. Okay, so I think that ends. So basically, that ends what I have to say about black holes. Right. So from next week, we're going to move instead of these exact solutions. So we're going to go to perturbative solution, which means that we'll go to flat space. We'll look at small fluctuation around flat space in terms of either talking about quantum gravity or in terms of gravitational waves. So these are all discussing first fluctuation around flat space classically, and then quantum mechanically. Okay, so that will be the topic of I think the next 2 weeks. Okay, so is there any questions?
I want to ask that for the when we are going to the killing horizon and then come back, why we need to separate the energy to E1 and E2?
Oh, the energy is conserved, right? So
Yeah.
The energy is conserved. So if I don't separate these two, whatever I go in, I come back out the same, right? Because energy is conserved, right? So the point is that the point is that I want to separate E1 plus. So it's just like momentum conservation. That's all that there is. So since energy is conserved, and then I separate into E2, the point is I throw E2 into the black hole so I don't see E2 again.
Okay, sure.
So E2 is going into the event horizon.
Yes.
And then I'm left with E1 coming out.
Oh.
But yeah, I mean, if not, sorry, I'm not sorry. Maybe I didn't reply you clear enough. But I don't really. What exactly is the question? So if we just have E, we just have a single object. We're coming in.
Yes.
And then we're throwing something into the black hole that must carry energy, right? The thing that is coming, and then we're coming back out, right?
Yes.
So at this point, before our world line splits, whatever E I have here, I have the same E here, right?
Yes.
Because this is the same geodesic, right?
Yes. Yes.
If I have the same E here, now, so that means if I have two things here, the energy is still conserved. This is still a conserved quantity. So I'm splitting things into E equals to E1 plus E2. E2 will be the thing that will be thrown in here. So E2 will be here, and the E1 is here. But because they were here, they were at the same geodesic, so this equality still holds, right? Before E2 is being thrown in, this equality is still hold. This equality holds at this point here.
Yes.
Right? So if I arrange such that, but the important point is that inside here, E can be either positive or negative. Okay, depending on how it's oriented.
Okay.
So that means I can choose my E2 to be negative. Then my E1 has to be positive. Sorry, of course it's positive, but it has to be the original thing plus an additional factor to compensate this E2, right?
Yes.
So if E2 is negative, then that means that E1 is going to be equal to E plus absolute value of E2.
Yeah.
Then your E1 comes out, and then E1 is actually bigger than E, the original energy.
Oh.
And
Okay.
of course, this is nothing fancy. It's just that here, yeah, it's just that the energy is actually going in. So that actually the black hole mass is actually decreasing. So you're extracting some energy from the black hole.
Oh,
But
so
yeah.
so what come out is just E1.
Yeah.
Oh, okay.
Yeah.
Okay.
But the important point is that you can do this because of two things. Okay. One is that you have this killing horizon, which you can go in and come out. First, we have an area where you can go in and come out. Second is that there is a conserved quantity, which is null here, and therefore changes sign from here to here. Okay, so because we evaluate that this is space-like, so we know that inside here this is space-like. Okay, if it is space-like, then that means that the energy component can be either plus or minus if it's space-like.
Yes.
Okay.
Yes.
So that's the. Is there any other question? Okay, very good. So we'll say goodbye to black holes until the end of the semester, and we'll go back to something that we're more familiar with, which is flat space. Okay. Okay, thanks guys. So I'll see you next week, if not tomorrow.
Okay.
Thanks. Bye.
Bye bye.